Leetcode medium questions. Okay, let me share my screen real quick. Okay. So today we are going through number of islands. For my question, for the first question, we are going through number of islands. Okay, so times n, 2D binary matrix grid, which represents a map of ones and zeros. Okay, so 1 meaning land, 0 meaning water. Sharing. Hold on. Am I sharing my screen now? Okay. Wait. Technical issues. Okay, this is new. Hold on. Let me get my other laptop because I'm using another laptop today, and somehow I think maybe the permissions are not right. You guys can read the questions first. So basically, what we want, what we get is a grid as an input, which is a 2D array. Okay, and they want you to return the number of islands. Okay, and we define islands by all of the ones that are side by side or on top or bottom of each other. We will define them as one island. So if it's diagonally connected, it's not considered an island. If only up, down, left, right connected, then we consider it as an island. Okay, hold on. Sorry, I apologize for this issue. Yeah, so for this question, right, is that we may assume that all 4 edges of the grid are surrounded by water. Alright. I don't know why it is not sharing. Okay, wait a minute, I'm turning on my other laptop. So today I'm going to use JavaScript because I've been using C++ for so many sessions. I'm just going to try to use something else. Right? And you guys can think about what approaches you guys can use for this. Then you can type in the chat first, then we can look at it. Oh, it's sharing now? Oh no, somebody else is sharing. Okay. Okay, yeah. Thank you. So you guys can look at the question and chat like what approach you can use. So this is a graph question, right? Obviously. Actually, it's not really very graphy, but it is considered as a graph. You can use some graph methods. It's just that you don't have to make like the adjacency matrix and all that because they already give you a matrix, right? So, has any idea what approaches you can use for this? While I turn on my other laptop. There are actually several approaches that you can use. As of now, I know that there's 3 approaches that I can use. But maybe there's more. So, I don't know. Anyone? Okay. So there's actually three approaches that we can use. So I'm just gonna put it in the chat first. Again, I apologize for this issue today. Um, so one is we can use one we can use depth first search approach. If you're not familiar with these approaches, you can easily look them up later. Second one, we can use breadth first search. And the third one may be a bit unfamiliar to some of you, but it's called union find. For me, I wouldn't use union find in this case because normally when there's coordinates, I don't like to use union find, but you can use union find. The three ways that we could, we could use to solve this question. So today, I think that I'm gonna do depth first search, and then if we got time, we can do breadth first search. Confirm no time do union find one. So, yeah. Okay. Hold on. Hmm. Okay. This is awkward. Okay. So, my laptop's super slow. Okay, maybe you can go into my Jamboard. I'll share it with you guys while I wait for my super old laptop to turn on. So, yeah, I guess I can start like explaining the logic behind that first search idea in the Jamboard first, and let's just hope that I'd be able to, have my laptop after that. Okay. So what we can do, right, is that, okay, for example, I have this matrix. Okay, with this matrix, I have, let's say, 0, 1, 1, 0, 0, 1, 1, 1, 1, 0. Okay, this is quite ugly, but what we can do is we can traverse the whole thing. I'm pretty sure that this doesn't add up, but whatever. We can traverse the whole matrix, right? And then when we meet a 1, we will sync the island. Okay, so for example, here, let me get another color. So here I'm traversing through this matrix. Okay, so this first one is 0, so I will just ignore it. Now I meet this 1, right? So I will sync this island. By doing so, I will check for its up, down, left, and right. Okay, basically doing a depth first search. And I will change all of the 1s to 0. So now I've already sank one island, right? So I can have a count. Okay, and the count would increment by 1. So now I have one island already. I will continue with all the other elements to check, right? And when I encounter another 1, I will sync that island again. So I will sync this island, and my count would increment 1 again. And has already been, so it's actually 0, right? So I would just continue, go on until I meet another 1, and I will sync this island as well. So I will make this all to be 0. Okay, and I will increment the count by 1. And so I will keep checking, and I realize that all of them are 0, right? So I will just check until the end. Okay, check until the end. And after I check until the end, I will know that I have actually 3 islands because I have count of 3. Okay, so the idea is to just go through the whole matrix, and if I encounter an island, I will sync it. And while after I sync an island, I will increase the count of islands encountered. All right. So this is the idea behind this question, right? So if you notice, this is we are doing depth first search because we are searching up, down, left, and right to find if there are any ones. Okay, so this is the depth first search approach. We can also do a breadth first search, which is very similar actually. Okay, but when syncing, right, we just use breadth first search to sync instead of like depth first search. So it won't be like recursive. Okay, so this would be my approach. Okay, my laptop's almost done. Give it another 1 minute. Okay, so this is how we can do it, right? So if we write some pseudocode, okay, so a bit pseudocode lah. Our first step is to traverse the whole matrix. Okay, the second step is if I encounter a 1 while traversing the matrix. Okay, so maybe I will just like put like that. If encounter 1, which meaning that I've encountered a land, right? Then I will sync the island. And I can do it using breadth first search or depth first search. Okay, but today I will be doing depth first search because most people we learn of depth first search first. It's more like basic. So if I encounter 1, I will sync an island using depth first or breadth first search. But today we are doing depth first search, and after that I would increment the count of island. Right, and then I would just using this logic to traverse the whole matrix, and then at the end I can just return count. Okay, so this would be our pseudocode All right, my laptop's ready. Let me switch it to there. Okay, I will disconnect for a while. Can you give some response if whether you can hear me or not? Okay, great. Finally. Sorry about that. I'll just share my screen now. This better work. Okay, yay! Oh, why is this so zoomed in? Oh wow, I did the C++ one before. Okay, but we're gonna do it in JavaScript, right? Oh wow, I did the JavaScript before. So. Okay, let me just discard this and we can reset to default. Okay, so according to my pseudocode, right, as mentioned just now, we can start coding. Okay, so first I'm gonna traverse the whole grid. Okay, so I can just row equals to 0. The length of grid. Okay. So here I'm going through the row and now I have to go through the column. Let me know if you can't see my screen. Yeah. Pretty sure that it's visible. Okay, so now I'll just have the inner loop to track the column. Okay, and since it's a column, it has to be grid at index 0. Right? Okay, according to our pseudocode, if grid at that position equals to 1, then I will sync it, right? So I can just make this if statement. If grid at row and column equals to 1, let me just put 2. Okay, if it equals to 1, then I will sync it. So how do I sync this? So this would be a separate function so that I can do the depth first search. All right, and upon syncing it, I will increment the count. Okay, and then at the end of everything, I will return the count. Right. So now let's work on the sync function. Okay, so I have a sync function, or I can just make it like that. You know, it's just EX6. Okay. Sync island. I'll just call this sync. All right. And for sync, I'm getting in grid as the parameter, and I'm also getting row and column. Okay. So in what circumstance do we need to explore its left, right, up, and down? Okay. What we can do is we can check for the current position at row and column. If it's a valid position, then we will continue checking. If it's invalid, then of course we won't check, right? So if it's valid, right, then we will sink the island. So we will change the land into water. So grid at row and column would equal to 0. All right, and we have to recursively check its up, down, left, and right. So I can just recursively call this, okay, with grid. And then I can just like move the row and column, right? So here I'm moving it down. Here I'm moving it up. And then I can move it down and left and right. Okay, so here moving it down. And then here I'm moving it to the right. And here I'm moving it to the left. Okay, so now we need to work on this valid thing. Like when will it be valid, right? We need to have some sort of indication, some sort of statement, right? So when does the value become invalid? Okay, if it's a water, then we don't have to search, right? So that's one requirement that we need to check if it's land or water. And another is that if the index go out of bound, right? If row is already 0 and I minus 1, it becomes -1, which is invalid. So I have to check for that as well. Okay, so let's just do that checking. So row has to be more than equal to 0, right? And then row has to be less than grid.length. Okay, and then column also has to be more than or equal to 0. And then column has to be less than grid at index 0 dot length. Okay, and lastly, we have to check if it's land. If it's not land, then why even check, right? Why even continue to sync it? It's already land. If it's already C, then you don't have to sync it. It's already sunk. So it has to be land. So I can just grid at row column equals to land, which is 1. Okay, so all of these combined together would be our requirement to keep searching. Okay, so meaning that if it is valid, okay, if the indexes are valid and if that position is a land, then I will sync it. Okay, and then at the end of this, I will just return. Okay, so since this is a void function, but of course, in JavaScript, we don't have to write like what values we return. We just put a variable. Okay, and here I did a mistake. I should be returning count, not incrementing it here. So okay, so going through the logic here, I'm traversing the whole grid, and if I meet 1, I will sync it, right? So here, the sync function takes in grid, row, and column. Okay, so I have to put in grid, row, and column. Grid, row, and column. Okay, so I will sync it first, and then let me see if I can open my Jamboard from here. Okay, fine. I can use this. Okay. So if we take this as an example, okay, if we take this as an example, okay, what we're doing is first we are traversing through this grid. Okay, first here we meet a land, so we will sync this whole island. Okay, so I will first turn this into 0 right here. So when I meet a land, I will sync it first. Okay, so by syncing it, I will check if it's valid, and if it's valid, I will turn it into 0, and then I will search for its up down right and left. Okay, so here I will change this to 0 first. Okay, and then I'll search for its up. Since its up is invalid, right? Because the row would be -1, it's invalid, so it wouldn't continue going. Now I'm searching for its bottom. So here, since it's valid and it equals to 1, I will change this to 0. And I will search for its up, down, left, right as well. Okay, so its up is already 0, so I will do nothing. Its down is 1, so I will check if it's valid. Since it is valid, right, it is a land, so I would turn it into 0. Okay, so you see what I mean, right? So for each value, I just keep checking up, down, left, right, and if it's valid, meaning that if it's a land, then I will sync it to make it into C. Okay, so now I've already sunk this. Okay, and I go up, so this is 0. Then I go up, this is 0. I go up, this is invalid. I go down, it's already 0. I go right, change this to 0. I go up, it's invalid. I go down, it's already 0. I go right, okay, it's 1, so I'll change to 0. Here, I'll go up, it's invalid. I'll go down, it's 1, so I'll change it to 0. And then I'll go right, it's already 0. And I'll go left, it's already 0. Okay, so the depth first search stops here. Okay, so this whole function will return. So I will come back here. Okay, and then I would increment the count. So now count equals to 1. I think I did not, yeah, okay, I did not initialize the count variable. So let me just do this. Let count equals to 0. Okay, like this. So now we have already sunk the island, but we are still at this first value of the matrix. So now we're just going to keep going on and checking. Since all of them are 0, so I would just go through all of them without thinking anything. And at the end, I would just return count, which is 1. So I'll be returning 1 here. Okay, let's run this to see if there's any errors. Okay, let me try submitting this. Yeah, okay. So this is the depth first search way of doing it. You can try using breadth first search or union find. Okay, breadth first search, you'll be using a queue instead of this recursive way, right? Usually for breadth first search, you'll be using queues. And for union find, you would have to create like the union function and the find function. Okay, and then you can just make a for loop here, right? And then you union all of them to, yeah, you just union all of them. And if they're already the same, right, then you can just like decrement it. So you start with, so for union find is a bit different. You start with all of the values. How do I say this? So if there's like 20 elements here, you start with 20 as a count for union find. Okay. Then first, you union the first two together. If you are able to union them, okay, then you decrement it. Every time you are able to union it, you decrement it. If you don't know what union find is, I don't think that you understand what I'm saying. But if you know what union find is, this is how you do it. And you can also check out union find online. There's a lot of tutorials about it. Yeah, but I wouldn't worry about union find a lot. I think most importantly, you have to get breadth first search and depth first search down first, be familiar with it, and then only you can start learning the others. Yeah, so that's pretty much it for me. I'm sorry about the technical issue just now. I hope that you still learned something about recursively doing depth first search for questions like these, right? So for these, we call these type of question flood fields. Am I still sharing? I think I'm still sharing. So there's also a name for it. It's called flood field, I think. Yeah, I think it's called this. It's basically the way of just checking up, down, left, right in a matrix. And you can always use this recursive way to check up, down, left, right while checking if it's valid or not. Okay, that's all from me. Thanks.
Okay, so it's my turn. Let me share my screen. Okay, so yeah, I'm sharing my screen now. For a problem that we're tackling today, it's a bit similar to just now. It's not very similar. It's just later we're going to do depth first search as well. But then the depth first search is not going through like a matrix or an array. We're going to do it on binary search tree. I think last week Mason has done a question on binary search tree. So I assume y'all like have a little bit knowledge on it. But I'll explain what a binary search tree is. Basically, it's a tree that can be done, that can perform binary search. Basically, that's the meaning. A tree that can perform binary search. So a binary search tree actually follows some rules. So what is a tree? So trees is something like you have like a very root, and then you have like different leaf or branches. So let's say in this, say okay, yeah. So let's say you can just take away all this. Okay, so let's say this is like a tree where the root is 2, and then the 1 and the 3 is the leaf. So like also like in a tree you have like branches, right? So how do we note branches is where, let's say I'll have like, let's say, let me make this bigger. Let's say there's a 5, this is 4, and then this is, okay, then maybe this can be 3, 2. This can what? This can be 4. Oh no, this can be 3. This can be 2, and this can be 4. Okay, then maybe I'll just extend here. Okay, then this can be 7. Yep. Okay, so this is a binary search tree. So okay, so this is the root. Okay, so the number 5 is the root, and then all the other things like 3, 6, 4, 7 we call node. So like the root is 5, and then every other thing is called a node. So like the tree is a node. So if I were to describe it, it would be something like this. So there will be like all of them are nodes, and then we can call a branch as a subtree, or we can just call it a branch. So on the left side, 2, 3, 4, I can just say this is the left subtree, which is 2, 3, 4, and eventually the right side of the root, that will be like the right subtree. Some people call them branches. You can like a left branch, or like right branch, but basically they have the same meaning, whether it's a branch or it's a tree. So basically this is the structure of a tree. But the thing with binary search tree is that there's some condition. If it has to be a binary search tree, it has to meet these few conditions. Number 1 is that it cannot have duplicates. So if you look closely, the whole binary search tree, there's a same element is not repeated twice. I cannot have like 1, 1, 3. It's not valid. Okay, you can have 1, 2, 3, but you cannot have like 1, 1, 3, because it cannot have duplicates. And then the left subtree must contain values lower than its root, and then this basically is the condition, but opposite. The right subtree must contain value higher than its root. So it's actually basically a binary search tree that contains these three condition. So the first thing is that it cannot have duplicates, and then the left subtree must contain value lower than its root. So what I mean, so let's say 5 is the root, right? And then 3 must be lesser than 5. I cannot have like 6 over, I cannot have 7 over on the left, because it must strictly follow that the left subtree must contain a value lower than its root. So let's say this is 3 lower than 5, so it's valid, and then 2 is lower than 3, it's valid also. And then the third condition is basically the same thing, but it's opposite lah. So the right subtree must contain value higher than its root. So number 4, it's bigger than 3, which is its root, so it's valid. And 6 is bigger than 5, valid. 7 is bigger than 6, valid. So basically this is the general concept lah of like a binary search tree. It's not that hard to understand. So it's quite important that we know this tree condition. Yeah. Yeah. Actually, they gave this condition also, like the left subtree of a node contains only nodes with keys less than the node's key. It's a bit confusing if you ask me. Okay, but you can just follow generally this tree rule. So this is a valid binary search. So what we want to do today is we want to validate whether a binary search tree is true. So how we're going to do that is that let's see the input. So they'll give us a root as the input. So let's say they'll give us a 5, and then we can actually traverse down the tree because every node has a left and right pointer. So I can go to the left pointer and go to the left subtree, and then I can go to the left pointer again and go to the 2. Okay, so basically what we want to do is we want to check whether the given binary is a valid binary search tree. So this is a valid one. So what about an invalid one? So we can just copy and paste one, right? And then, oh wait, it doesn't work that way. Okay. Okay, so this would be an invalid one. So I can just maybe annotate this valid. Okay, and then this one is invalid. Okay, so basically this is like the general idea. So we'll have this is valid BST thing. We have to implement this function where this function will check whether the whole binary search tree is valid or not. So how can we do this is where we can perform a depth first search. So remember, depth first search is it's something that you go down, follow its path until it cannot be down anymore. So we can just check it like in this way. So like let's say I start from 5. So I want to go to the left first. It's up to you whether you want to check the right because all that you have to do is you have to make sure all these 3 conditions is met. So actually if we make sure these 2 conditions it will never have duplicates one because it cannot be equal. So it say must contain value lower. It doesn't say lower or equal to. So if we meet these 2 conditions, the first condition is automatically met. So we just have to check for these 2 conditions. So let's try to move on. So let's say we start from the root, and then we look at the left subtree. Okay, so is 3 is 3 lesser than 5? Yes. Okay, move on. Okay, is 2 lesser than 3? Yes, move on. So is there a next element after 2? So there's no next element after 2. So I'll just go back, depth first search, right? So I'll go back to its root. Is there a right subtree? Okay, yes, there's a right subtree. I'll check. Okay, is 4 bigger than 3? Yes, so it's valid. So I'll move on. So because here there's nothing left already, so I go back to the root. Okay, then I check the right subtree. Okay, is 6 bigger than 5? Yes, correct. And then is 7 bigger than 6? Yes, correct. So everything is correct. So then I return true. So it's a valid BST. So for the invalid one, we go about it the same way. So let's say I'm starting at 5, and then I check the left subtree first. So is 8 smaller than 5? No. Then straight away I can return false because I know the left subtree must be smaller than the root. So let's say if we have another example like this, let's say like this Okay, so this is also invalid. I'll just check. Okay, is for starting from 5, is the left subtree value smaller than 5? Yes, correct. Continue. Is 2 smaller than 3? Yes, continue. Is there any element after 2? No. So I go back. So I go back to the root. Okay, is there a right element? Yes. Is the right element bigger than 3? No. It's not bigger than 3. So this is invalid. And I'll just return false. So basically this is what we'll do with the depth first search. It's not that hard to understand. It's just that part where we have to implement it. So in order to do this, we're going to use recursion. I'm pretty sure there's a way that you can do it without recursion, but it's much easier to understand in the recursion way. The code is much more simpler. So I'll have to first define it first. So let's say I need a function. That function will validate whether rack node or not. So for this one, I'll have to take in the. I wanna check range because I know every time when I do a comparison, There's always a range. So like when when I'm at the root number, like at the root, which is 5, and I'm comparing 3 with 5, right? So in this case, I know for sure that the maximum it can be is 5 because it cannot be bigger than 5. Yeah, it must be smaller. In other words, it cannot be bigger than 5. So the 5 is the max. And then the minimum value, it doesn't has like a minimum, it doesn't matter because it can be any number lesser than 5 unless it says, yeah, the number of nodes, yeah, it says like it has to be like negative 2 to the power of 31, but it actually doesn't matter. As we know that it can be any number, so we don't have to set for the minimum, but we have to set for the maximum because the maximum is 5. So so we need a maximum value. So let's say max, and then we also mean first, and we need also what is it called? We also need the what? Yeah, we also need the maximum value and the. So basically, this is two things that we need. And then, so how do we check? So we have to like the check first. We all has a base case now. When you're doing recursion, you all has the base case. So how do we know is the base case? So if we look at this example, how do we know we actually traverse all of the nodes already? Is where we know that there is no next element. Like the next element is null, so we know that suppose that we should stop. So that's the part where we should stop. So we should have to wait one. Let me drink water first. Okay. Yeah. Okay. So first one, we want to check. So for the base case, we actually want to check whether we reaches the end already or not. So how do we know if it's the end? Because we know that if you look at the above definition, the definition for left and right is a pointer. So we know if it's if the pointer, if it's null, because it's a pointer, and then like the root is also a pointer, so we can check whether it's a null value. So I can check whether if root is equals to pointer. If it is no pointer, then I can just return true, because when I reaches the end, okay, when I reaches the end here, that means I already like I know that it's valid because I reached. So so the other condition is we want to do something like so maybe I can just write the let me just make this more clear. I'll write this. Okay, so this is the base case, and then if we successfully the end, then we know it's valid, right? Okay, and if we haven't reached the end, we want to check if the node is valid by seeing if if its value stays within the range. Okay, because this validate function is where we'll pass in like a minimum and a maximum, then we just check whether it's in that range. This is quite simple. So if there's a max and the root value is bigger or equals to max, then we know it's valid. Okay, so that means what it means, like if max is defined, okay, because this is a pointer. So when I do max and actually saying like if max not equals to, but we can just not like ignore that part. We don't have to write that. We can just say max and the value is bigger or equal to max. That means like if like I'm checking 3 and 5, right? So 5 is, so if 3 is bigger than 5 or equals to 5, then I have to return false, because if this is, let's say this is 5, then this is invalid, or let's say this is 6, this is also invalid already, so then I have to return false. So this is the first case. Then there will be a second case also, because like I will also have to check for the, so if mean is defined and the value of root is smaller or equals to mean, I also have to return false. So what does this mean is where, let's say, when I'm checking, let's say, like I'm checking the right subtree. Yeah. So the minimum value is 5, and then I'll check like, okay, is 6 smaller or equals to 5? No, so this is valid. Let's say if this is, there's a 4 here, so the minimum is 5. So if I'm checking, okay, is 4 bigger than 5? Then it's not right, so it's invalid. So yeah, so basically this is the key. If the value is smaller or equals to 5, I'll just read. So that's, and then else, I'll have to do the recursion here. Okay, else, I will just write it in simpler ways. I have to, so basically part is where, let me just write that first, then I'll have to validate the left subtree, and then the value of the left subtree, and then mean. Okay, and I want to check whether let me just write this out. Okay, it's probably complicated. Try to explain. I'll try my best to explain this. Okay. Maybe I write it in a simple text that easier to understand. Okay. So bool is left subtree value. So I want to check like the left subtree. So I'll pass in the left node, and then I'll pass in the value of the left node. I have to do this like I have to do this like 10%, whatever. It's because I want to pass in point. So it's the reason. It's because I want to pass it. That's why there's a 10%. So this call, this recursive call, will check whether the left subtree is valid. So I'm at 5, right? So I want to validate whether the left subtree, like pass in the tree, and then check whether this whole thing is valid, and then I'll have like is right subtree valid. So I'll also do almost the same thing, but instead of like oh sorry, so I actually should check for the value here. Okay. So then this part would be for the max value. Okay. So let me try to. So in the end, I have to make sure that the left subtree is left subtree valid and it's right subtree valid. Subtree, yeah. Okay. So I have to return this. So basically, let me leave some comment here. Check the left and right subtree recursively. So because this is what we are trying to do. So basically, I'll just like explain it one more time. I think it's not very clear. Okay, what I'm doing is I have a root, right? I have at 5. So I have to check this whole branch or this whole left subtree 3, 2, and 4, whether is this all a valid one. So if this is all valid, then I know I completed half of the work. Then I have to check whether the right subtree is valid. So if the right subtree is valid, then I completed like the other half of it. So if both of them are valid, if the left subtree is valid and the right subtree is valid, then I know that the whole binary is valid. So basically we divide the problem into half. So I want to check the left subtree first, then I check the right subtree. So only both of them are valid, then I'll say like I'll conclude that the whole binary search tree is valid. So basically this is the idea. So when I first call this function, so because the validate function is the value, so I can just make a call to validate. So I'll first pass in the root. I start from the top. So I know that at first it wouldn't be, it would just, the reason why is when I'm like at first I don't have like a minimum or maximum value, because if you think about it, the whole flow when I call this function, it will get down here, and then we check if 0 is no pointer. It's not, right? Because it's 5. It's not no pointer. So we wouldn't return. And then this case will not occur because it checks first whether max is defined, and then it checks whether min is defined. But in this case, it's both of them are not defined. So we go to else. So at first, if I put no, that means it will come to this case where it will check left subtree, check right subtree, and then all this base case and this part, it's for the recursive call inside where we check like the left subtree and the right subtree. I hope I make it clear. Let's just try to run this. Let's see if it's correct. Oh, use of fun. Oh yeah, okay. My bad. I should actually how to say? Maybe I can put this in. See if it works. Yeah. Yep. Okay. So it works for this one, but let's just submit it and see if it works. Yeah, and it works fine. So basically, this is the idea. This is the whole idea of like validating a binary search tree. Yeah, I'm not sure whether I'm clear. Is it? Anyone has question on this? Is it clear for the solution, or you need further explanation? Because yeah, that's the. I'm just afraid like maybe it's not really clear. But anyways, just remember, like for binary search tree, it will always just ask you to traverse the tree. So the most important thing is you have to understand what a depth first search is and how to implement depth first search. Like Mei-Sing introduced to you all last week, there's two ways to do a depth first. You can do it iteratively or you can recursively. But normally recursively would give you like a much simpler code. Because like I can actually refactor this code. I can just say, if I want to make this like even shorter, I can just say return this, and I can just do this. Yeah, then this whole thing will still work the same. I mean, it's not that much of a code lah. When you implement like depth first search, it's like 3, 4, 5, 6, like 6 lines of code. You've implemented a depth first search. Of course, if you want to do this with a breadth first search, it's possible. You can do breadth first search, but I would say doing depth first search is much faster and also it's much simpler lah. The algorithm to like do depth first search, because depth first search is very very easy to understand, where you just go down and then go down and then go down and go down until you cannot go down, you come back up. So but breadth first search is where you want to check horizontal. So like to me the biggest difference for a DFS and a BFS, where when you're doing DFS you keep going down like 5, 3, 2, okay, cannot anymore, and then I come back and then I go the other path. So that's a DFS. But for BFS you check like, okay, 5 and it's 3 smaller than 5, okay, it's 6 bigger than 5, okay, both of this part valid, move on. It's 2 false, and then it's 2 and 4 a valid like child of like 3, and then it's 7 a valid child of 6, okay, correct, move on. So like that is the part for like BFS. But in this case I just think that like the DFS solution is much simpler to write. Yeah. And oh yeah, for this solution, right, the time complexity and the memory complexity is actually O of n. So O of n, and space complexity, it's also O of n. Okay, why the time complexity is O? Because in order to validate in order to validate the, we actually have to traverse to all the nodes. Because look here, we actually check every node whether the node is bigger or smaller than min, because like all the child nodes are, it's actually checked first, then we like determine that this is a valid binary search tree. So that's why the time complexity, and because we have to do the same amount of work for every node. And the space complexity here, although we did not use like additional memory to like allocate an array or something, we didn't use like extra memory. But in this case, because it's a recursive call, if you know about there's a you call like a function stack function. There's two type of memories. Like if you, especially in C++, there's something called the heap memory, and then something called the stack memory. So when you call a function, essentially what the computer is doing is it's pushing something to the stack. It's using the stack memory. It's pushing something to the stack when you are like executing. So because we're doing recursive call, right? So we'll occupy the stack for the whole amount of like O of n. Like when we do it, like because when you call a function, it doesn't return yet. Like then you call another function, then within it call another. The at most because we do validate on every element, so at most we'll like allocate a function call, which is a validate function call for each element. So there's like n elements. The space complexity is of n. So that's the reason why the space complexity is of n, even though we did not use like any array. So or any like extra memory. That's the reason. So I think that's all for today. Is there any other question? Maybe I want to do this first. I want to have some feedbacks. Is it understandable for the explanation? Okay, I'll just cause okay. It's okay. Yeah, it's understandable. So I think it's good lah. It's good that it's understandable. I'm just worried that it's not too hard to understand. So if that's okay, then I think we're done for today. Yep. We'll see you all next week then. Okay. Thanks for coming. Bye.